So how many problems are over in this? Okay. Those who are online, are you able to hear me?
Yes, sir.
So first one is over and second one is over, right? Okay. For third one, let's see. Let's recollect. So you are able to see that there is a coil. This is a current carrying coil, and you have a loop present. Okay. When this closed, when you close the key, right, then how is the current in the coil going to be? So thing is, you have to first look at the center. So whichever side you are able to see the center, you mark your eye there. Okay. So when you see it from this side, is the current revolving in clockwise direction or anti-clockwise? That's right. Yes. So when you see the current is revolving in the clockwise direction. So when it is revolving in clockwise direction, then when you close the key, right, is the I value increasing or decreasing? Is the I value increasing or decreasing? It is increasing. If I is increasing, B is also increasing. So when the magnetic field is increasing, flux will also increase. When everything increases, the side that you face will have the same pole or the opposite pole. Hey, if it increases. Yes, same pole, right? So this side you are able to see south pole because the current is in the clockwise direction. So what you get generated, this side it is the same south pole, but which side are you able to see? Are you able to see the back side or this side? So you're able to see on the right hand side. That is the side where the common axis is written. Guys, those who are online, I hope you're able to understand what I'm trying to say. Right? So if one of the sides is south pole, then the other one will be north pole. When it is north pole, what is the direction in which current is going to revolve? Anti-clockwise. So the answer will be X, Y, Z, X. Make a note of this. X, Y, Z, X. Right. Do the next one. Can we go a little fast? So do the option D1. So the rheostat is there, right? Is your rheostat move towards the resistance of increasing value or decreasing value? Observe this. Observe this. When you're going right, you're going closer to the side of the wire. So rheostat works on the principle of R is equal to rho into L divided by A. Means more is the length of the resistance that is involved, then resistance will also become high. Okay. So since you are moving it towards the end of lower resistance. So where are you moving? You are moving it to the end of lower resistance. What you can say is the resistance is decreasing, means current is going to. So if resistance is decreasing, current will increase. Current increases, magnetic field will increase. If magnetic field increases, flux will increase. I already told you in the previous class, you should always start looking at the coil from the side where you're able to see the center. So for the second part, in this case, where will you see the coil from? You'll see it from here. Is it right? Now, when you see it from this side, what is the direction of current? Anti-clockwise. So this acts like north pole, right? So first thing found, flux is increasing. What pole will get generated? Same pole. So this will be north. If this is north, what is there on the other side? South. So south means you are able to see the center of the coil. Means when you see from this side, you are able to see the center of the coil. So south pole means what should be the direction of current? Clockwise. Clockwise means Y, X, Z, Y. That is the answer. So this is the trickiest part. This is what you need to master. I hope I'm clear, right? Right, next one. What answer? How to do this? Nitish, tell me. So when the tapping key is just released, so when you're releasing the key, what is going to happen to the value of current? Current decreases. Current decreases. Magnetic field decreases. Magnetic field decreases. So all are directly proportional, right? So now we need to see which side is north pole and which side is south pole. For that, observe the direction of current. So what is the direction of current? When the key was closed, the current would have gone in this direction, right? So when you see from this side, what is the direction of current? Anti-clockwise. So anti-clockwise means this will act like north pole. So flux is decreasing. So this side will be south pole. If this is south pole, what is the other side? Why did I take the other side? Because I'm always trying to see from the side which is visible to me. I'm always seeing from the side where the center is visible to me. So if this is north pole, what is the direction of current? Anti-clockwise. Anti-clockwise, now what is the value? Correct yourself. It is XRY, XY. When the current is going right, this current is actually entering to the subsequent loop. It is entering to the subsequent loop. When that is the case, current will first come out of here and it will go to R and then it will come to Y. So XRYX is the answer. Okay, next one. Current I decreasing at a steady state. So if the current is decreasing at a steady state, what is the direction of magnetic field with respect to a straight current carrying conductor? For a straight current carrying conductor, the magnetic field will be in the circular loop, right? So when the field and the areal vector, so field is along the circular loop and areal vector is perpendicular to the circular loop. When that is the case, what is the value of flux associated with it? I repeat my question. Magnetic field is along the circular loop. Areal vector is perpendicular to the circular loop. Then what is the direction of, what is the value of flux associated with it? What is the value of flux associated with it? Nobody can give you a better hint. Huh? 0. BA cos theta. Theta is how much? Magnetic field and areal vector are perpendicular. So the flux that is associated with this coil is 0. When the flux itself is 0, who is bothered whether the current is increasing or decreasing? So when can you generate EMF? Only when there is a change in flux. Flux failure, then what change is going to happen? Okay. So this is a tricky question. Mark it as important. This kind of a question will definitely come for 1 mark. Okay. So I don't know what is the pattern. I repeat it again. But when it used to be subjective, this question has come many times. Okay, this is an important one. So mark it as important. And I hope everybody understood this. Right? Those who are online also, I hope you understood this. Right?
Yes, sir.
Yes, sir. That's right. Perfect. Okay. So we'll do one last problem that is based on Lenz's law. Then we can step into the next important concept. Okay. So I hope it is not tough, no? Is it? Okay. So I want you guys to do this. 6.2. Harshvardhan, are you there?
Yes, sir.
Can you try the option A1? 6.28. Can you try it? I'll help you if you get stuck.
Yes. Yes, sir.
Yes. Tell me what is the answer. So what is the question? Use Lenz's law to determine the direction of induced current. So read the question carefully. They are asking the direction of induced current in the situation described by figure 6.19. There is a wire of irregular shape turning into a circular shape. Okay, that is the question. So what is happening? There is a wire of irregular shape which is being turned into a circular shape. Circular is a regular one. So what are the parameters you are supposed to check? So then can you tell me? Flux is what? BA cos theta, where B stands for magnetic field, A stands for the area, magnitude, right? Area. Then theta represents the orientation between the magnetic field and the areal vector. Is it right? Now the question is, in this case, is the magnetic field changing? For sure. In this case, is the magnetic field changing? Anybody? They put an into mark, right? They didn't mention anything about magnetic field. Then you can conclude that it is not changing. So magnetic field is constant. What about the areal vector? Area is changing. Right? Is the area increasing or decreasing? So when it goes from an irregular shape to a circular shape, is the area increasing or decreasing? It is increasing. When area is increasing, flux is increasing or decreasing. So in this case, what I will write is area is increasing. So flux is also increasing. When flux is increasing, then what pole will get generated? Same pole. Now comes an important question. Look at the direction of magnetic field. So you're looking at your paper, right? Your textbook is here. You're looking at the paper. Is the magnetic field received by the paper or is it emanating from the paper? paper idra. How's mark on the paper? Is it an into mark or a dot? Into na paper is receiving the field lines. Idra, this is not a dot, that is a circular shape. Look at the other parts. Into irka. Okay. So it is an into mark. Now the question is, so paper is receiving the field lines. Means what is your paper acting as? Is it acting like a south pole or a north pole? Think and tell me. Which pole has a tendency to receive the field lines? South pole. So your paper is acting like south pole. So your paper is acting like south pole. Who are you? So you're the one who is looking at the paper. So you're north pole. So what is the coil facing? The coil is facing you. The coil is facing north pole or south pole? Obviously you do. So I come from the beginning, listen to this. These are the steps to be followed in these kind of problems. So there will be two kinds of problems which will be asked based on Lenz's law. One is 6.1. If you see in 6.1, what was the parameter that was changing in every problem? It is the value of current. So due to the value of current, you had a change in the magnetic field, due to which there was a change in magnetic flux. Whereas in this case, what is happening is magnetic field is constant and orientation is constant, but area is changing. So whenever you have problems where area is changing and you are asked to find the induced EMF, the first thing that you're supposed to do is define yourself of which pole you are. So in this problem, in case A, which pole are you? Your north pole, and the coil is facing you. Okay, so coil is facing north pole. Second question to be answered. When the area changes from irregular shape to a circular shape, area is increasing or decreasing? Increasing. Flux is increasing or decreasing? Increasing means same pole will get generated or opposite? Same pole. Same pole as whom? As what you are. So same pole of what you are now, what will get generated? North pole. So if this is north pole, then what should be the direction of current? Anti-clockwise. So DCABD is the answer. Sorry, yes, DCBAD is the answer. Is it clear? So this is how it works. Those who are online, are you able to understand what I mentioned?
Sir, you mentioned since the paper is receiving the magnetic field, it is south pole.
Yes, paper is receiving the magnetic field lines, hence it is south. Okay. So did you understand the flow that you are supposed to follow? So listen. What about option B? I want you guys to try it. So those who are sitting here, for your board is the paper. And those who are looking at your textbook, your paper is the, your paper is obviously your paper. In this case, what is happening? See, it's very simple, okay? Let's not go with left hand rule, right hand rule. I'll only think of few points. I'll first look at the magnetic field. Is it coming out of the plane or going into the plane? Out of the plane. So what is your paper acting as? North pole. So who are you then? South pole. So have that in mind, your south pole. So that circular coil is there. The circular coil is changing from a circular shape to whatever shape you call this as. Okay, for capsule, when it is getting changed. So area is increasing or decreasing? Decreasing. So what will happen to flux? Flux will decrease. So flux decreases, it will be opposite pole of who you are, your south pole. So what pole should get generated? North pole. So north pole, now what should be the direction? That's it. D dash, C dash, B dash, A dash, B dash. Done. See, as of now, I have not taught you how you're supposed to write. See, I'm explaining a concept, right? You're able to understand and follow that pattern. But there are certain ways in which you need to write it in the exam that I'll teach you later. So you first concentrate on how to solve the problem. So you should not write we are not pole, that is why you should not write it. Yeah, they expect some keywords. First you master this, then I'll tell you. right? So I hope you're clear with both the basic concepts that are related to this chapter. One is you need to know magnetic flux. If there is a change in magnetic flux taking place, there is going to be an EMF induced. And that induced EMF will cause an induced current. And till now, we tried to find out what is the direction of induced current. But having said this, the whole chapter runs, see, since the name of the chapter is electromagnetic induction, the whole chapter runs only on one concept. What did I tell you? Change in flux. What flux? Magnetic flux. So only thing is that point. But now I look at the mathematical equation. I am able to understand the fact that magnetic flux is dependent on three parameters. What are they? Magnetic field, area, or orientation. The theta. Theta is the angle between magnetic field and area. Whenever they change the parameter, right? Whenever you want to change the flux, what is the logic is? You look at it like a function. Okay, whenever I want to change the value of flux, what can I change? I can change B, I can change A, and I can change theta also. But if I do everything simultaneously, right, it is complicated for us to apply it. If you ask me, can I do that? Yes, you can do that. But you need better mathematical tools to handle it. In the sense, you need to go with calculus, which is not a part of our headache at this point of time. That is why what they did is they keep two parameters constant and change only one parameter. That is how the concepts vary. Right? They can either keep B constant and A constant and vary the orientation. That is how your generators work. You have heard of the AC generator, right? So AC generators work on the concept where orientation is changed. Secondly, there is a place where magnetic field and orientation are kept constant, but aerial vector is changed. Like how these problems are there. And the third case is obviously you keep area and orientation constant and you change magnetic field. So to change magnetic field, generally we can't do it directly. We change the current, and current will change the magnetic field. Right? So this is how the topics are classified. Now, based on this logic, what happens is there is another EMF that will get generated, which happens due to, I'll come to the point just a minute. Yes. So there is an EMF that will get generated due to motion of a conductor. Why is it happening? Due to the motion of a conductor. And that EMF which is getting generated due to this motion is called as motional electromotive force or motional EMF. So this is the next topic that we are going to discuss. So can you please write down the heading? So the heading is motional EMF. Okay. Tarush, I hope I'm clear. You're tired. Want to wash your face? Listen. Suppose I have a rectangular shaped railing, which is a frame basically. I have a rectangular shaped metallic frame on which there is a conductor placed like this. Right? There is a metallic frame on which a conductor is placed where the frame is fixed, whereas the conductor has a provision to move left and right. Okay? Like how it is shown in the diagram. So if that is the case, I'll call this as the metallic frame, and this conductor is called as, conductor is obviously the conductor only which has the tendency to move, right? To take this whole system, when I say whole system, the frame plus the conductor, and put it into a magnetic field, right? So that magnetic field is a constant. So generally when they give you only into mark or a dot, right, remember they are always constant magnetic fields, right? Now what is happening in this scenario is, it is because of the conductor. Actually, what was the frame shape? C shape. C is an open shape or closed shape. Basically, if you take only C, it is an open shape. Open shape can be defined flux. For you to define flux, what you need? You need magnetic field through a given area. Whereas when I say open shape, right, can I define the area of it? It is infinite. We don't know what is the area, right? So to close it only, what they did is they put a conductor on top of it so that it took the shape of a rectangle, right? Now what are they doing is keeping the frame fixed. When they move the conductor to the left and right, can I say that the amount of flux that is associated in this region is changing? Think about it. I shaded a particular portion, right? Can I say that the flux associated within within the rectangular tube is changing as the conductor is moving from left to right? Can I say that? Yes. When that is a scenario, listen. If I take the length of the metallic frame to be L, and I say that the conductor from the fixed end of the frame is at a distance x. Okay. Now you guys tell me one point. I'll zoom it. So you're able to see L and X. Now you guys tell me which of the two parameters of L and X are changing with respect to time? X. L is constant. It's a fixed surface. So can I say that the flux associated, what flux? Magnetic flux associated with this coil is equal to B into L into X. Can I say that? Yes. Now if I differentiate this, what do I get? B into L into dx divided by dt. Then what is this dx divided by dt called as? What is rate of change of distance or displacement? You can either say velocity or you can call it as speed in this case. Because I've taken x, I didn't take x as a displacement, I took it as distance. Okay. So when this is the scenario, 1 minute, I'll do one thing. I'll write the steps again. This is an important concept. Okay. I hope I'm clear till this step. No confusion. No? You understood the system's arrangement? So the flux associated with the region, which region? PQRS within the region is equal to B into L into X. How did I write B into L into X? Because B is the magnetic field. What is the basic formula? B A cos theta. B B only. What is the area? Length into breadth. Okay. What is the orientation? Theta is 0 or 180. So when you talk about a two-dimensional shape, it can either be 0 or 180, but most probably we'll take it in the direction of magnetic field to make our job easy, right? So when this is a scenario, if I differentiate on both the sides, d phi by dt, then what is it going to be? B into L into, because I told magnetic field is constant, length is also constant. So what is changing? X is changing. So dx by dt. This can I call it as BLE? And what is this d phi by dt called as according to Faraday's law? This is what is called as EMF. So the motional EMF associated with this coil is as simple as an expression B into L into V. This is not a simple derivation. This is the simplest you would have seen, right? Only 3 steps. So it is B into L into V. Now I am going to explain you about finding the direction. So first make a note of this. Shall I proceed? Yeah. Shall I proceed? Now see. How to find which pole is positive and which pole is negative? Which end is positive and which end is negative? So in this scenario, if you see, is the flux decreasing or increasing? So I told you there is also a case where area is changing, magnetic field is constant, and orientation is constant. Right? Now the thing is, which pole are you according to this problem? Which pole? Which pole are you? So you're the north pole, and the flux is decreasing. When flux is decreasing, what happens to the pole that will get generated on the other side? Opposite pole. So it should act like south pole. So when it is south pole, right? What is the direction of current? Clockwise. So current. That's why they gave the direction of current as clockwise already. So when the current is in the clockwise direction, which pole is positive and which pole is negative? I want you to be very careful with this. Don't wash your face. Water. See, why are you people getting so tired? What is the problem? Mask. Faces are sleepy. What is happening? Exhausted. Exhausted. You're also tired. Yeah. Too much of work. Yes. What were we discussing? The current is the clockwise direction, and mask also is a problem actually. Your oxygen levels will be slightly less. Okay. So what about Q? Which pole is positive, which is negative? Current flows in the clockwise direction. Current flows from higher to lower potential. So which is higher and which is lower? Which is higher and which is lower? I'm saying Q is at higher potential and P is at negative potential. That is why the current is flowing in the clockwise direction. So remember this point, the current flows from higher to lower potential outside the circuit. I mean, so this is acting like a battery. Except that only across the battery you are going to have that EMF. Okay. Current flows from higher to lower potential outside the battery and lower to higher potential within the battery. So that is why it is working this way. Is that clear? Right? So this is what happens. Please make a note of this. Write down the logic. Clear? Okay. Now I want to answer the same question using another logic. Okay. So let's say the magnetic field is into the plane and you placed a conductor into it where conductors have 3 electrons accepted. And in this scenario, the conductor is moving in the leftward direction. Is that right? Now, what is the force experienced by the electron? So, what is going to be the force experienced by it? Force is equal to QVB, where Q is how much? E. V is V only, and B is also B only. So, EVB. But now my job is to find in the direction in which the force is acting. So how do you find the direction? So what did they apply in the first place? Where did this QEB come from? What is the name of it? What force is that called as? It's called Lorentz force of magnetism. So when I say this is the Lorentz force, the point is, what is the direction in which the Lorentz force is acting? Yes, it is C. I'll write it again. Can I write this as Q into B vector cross B vector? So Q is what? E, but with a negative sign. Multiplied with what is B? B minus I cap cross what is B? B minus K cap. Is it right? So minus EVB into minus I cap cross minus K cap. So what is I cross K? Minus J. So you minus J. Yes. So minus EVB into minus J cap. So minus of minus, what will it give you? EVB in terms of J cap. So what is it you're able to understand? Due to the motion of the conductor in the magnetic field happening in the leftward direction, the free electron that is present inside the metallic conductor experiences a force in the positive Y direction. Is that right? So when it is experiencing force in the positive Y direction, where will this electron go and sit? The electron goes and sits at this end because it is experiencing more of force in the upward direction. So more amount of more density of electrons concentrated at the top will give you what kind of a charge? Will give you negative charge. Obviously, the other end will be positive charge. Is that not what I've written here? You're able to understand, though you try to explain the same thing in trying to find the polarities of each end of the conductor where the EMF is generated, whether you follow the concept of Lenz's law or whether you follow the concept of Lorentz force, it will give you the same result. Okay, so please make a note of it. Is it clear, guys? Right? Those who are online, are you clear?
Yes, sir.
Okay. Shall we do a problem based on this? So whatever problem I'm going to explain now are very, very important. So read this question carefully. There is a metallic rod of length 1 meter. And this rod is rotated with a frequency of 50 revolutions per second or rotations per second, whatever you call it. with one end hinged at the center and the other end at the circumference of the metallic ring of radius 1 meter. Can you try drawing the diagram for this? See, they have given figure 6.11, keeping that aside. Can you try drawing the diagram for this? The information given in the first sentence, or I call it as first phrase. Can you try? So there is a metallic rod, okay, and the length of the metallic rod is 1 meter. Okay. It is rotated with the frequency of 50 revolutions per second, with one end hinged at the center. So one end is hinged at the center. Arvind, try to draw the diagram. Don't look at the book. So one end is hinged at the center. So you know what will happen? What shape? They've given. So there is a metallic ring that is present. So first draw the metallic ring. So you do the metallic ring. For that you have a center, right? So at that center, what is happening? One end of the rod is hinged. Now the important question is, the rod's length and the radius of the circle, are they the same? Yes. Means where is the other end? The other end is exactly coinciding with the circumference. So based on this, can you draw it? So draw. So first draw a circle. At the center, from the center to the circumference, draw a rod, a small rectangle. Yeah. Now read the question. And it is rotating about an axis passing through the center and perpendicular to the plane of the ring. So if this is the ring, then if the center is here, the ring is revolving in this direction so that the plane is perpendicular. So that the axis is perpendicular to it. Plane of the ring is perpendicular to the axis. It's rotating about its natural axis. Is it clear? Right? When that is a scenario, there is a constant uniform magnetic field of 1 Tesla, which is parallel to the axis, that is present everywhere. Right? Now our job is to find the EMF between the center and the end of the metallic ring. That is the center and the metallic ring. That's it. Did you guys guess the diagram by now? So it is going to look something like this. So you have a circular ring. To that circular ring, you have a rod which is of 1 meter length, where one end is hinged at the center and the other is revolving about the circumference. So let's say it is revolving in the anti-clockwise direction with an angular frequency of omega. What is given here? Have they given the angular frequency or just the frequency? 50 revolution per second. So they only gave you the frequency. How do you calculate the angular frequency? So omega is equal to 2 pi f. Right? So 2 pi into 50 is going to be 100 pi. But now it is not going to be revolutions per second. It is going to be radians per second. Is that right? No? Let us say the rod has got revolved through an angle theta. How much has it got revolved through? Through an angle theta in time t. Okay. Now, what is the small amount of flux that will get generated? One minute. So what is the small amount of flux that will get generated? So d phi will be equal to magnetic field into area swept by the coil into cos of the orientation. Orientation in this case, I'm calling it as alpha because the rotation it has made is theta. Are you able to understand the difference between theta and alpha? Theta is the angular displacement, whereas alpha is the angle between B and D. Okay. In this case, what is the value of alpha? They gave an important point in the question. Did you all read it? A constant and uniform magnetic field is applied parallel to the axis. Parallel to the axis means parallel to the aerial vector also. So what is the value of alpha? 0. So this will be equal to B into A. The reason why I wrote it as d phi is because instead of writing it as A, I will write it as dA. Okay. What is the small amount of area it would have swept? See, it's very simple. Okay, let's not pi r square. So how did we get that? So when I say it has revolved through an angle of 2 pi radians, what is the area that gets covered? Pi r square. 360-degree revolution or 2 pi radian revolution will give you an area of pi r square. Now it has revolved through an angle theta where theta is in radians. Then how much would be the angle swept by it? Sorry, area swept by it. Theta by 2 pi into pi r square. So it's not a formula. So basically it is half into r square into theta. Okay. So what is the value of d phi, guys? D into 1 by 2 into r square into theta. One small correction, I made a mistake. It is not d phi, it is phi only because it's a measurable area. I never told theta is very small. Just want to make the correction. It is only b into a and area is half r square theta. So this will give you phi is equal to b into half into r square into theta. This is clear till this step. Is it clear? Now what is our job? To find the magnitude of EMF. So how do I find the EMF? How do I find the EMF? d phi divided by dt. So d by dt of half into b r square theta. So half b r square, if I take out, d by dt of theta is how much? Half into b r square into omega. Because d theta by d phi is what? Rate of change of angular velocity is, sorry, rate of change of angular displacement is angular velocity. So half into b r square omega will be the answer. So this is the value of EMF. So 2 points to be noted. This is also called as motion EMF only. So when the conductor is in linear motion, what is the value of EMF we got in the previous case? First listen, then you can write. So in the previous case, when the conductor was moving in a linear motion, what is the value of EMF we got? B into L into B. Whereas if the same conductor is revolving in a circular path, then what is going to be the EMF? It will be B R square omega divided by 2. So this can be used like a formula also to solve other problems. So clear? So half B R square omega will be the answer. Right? By any chance, can you find the direction of EMF? I mean, can you find out which pole is at positive and which is at negative? Among O and P, which end is at positive value and which end is at negative? So I already gave you the concept of Lorentz force. So using Lorentz force, find it out. Center will be negative. Check. According to you, is the rod revolving in anti-clockwise direction or clockwise? Anti-clockwise. Then correct yourself. Center will be positive because it's very simple, guys. Listen. This is the direction. This is O, this is P. Okay, according to you, this is O, this is P, and the coil is revolving in this direction. Anti-clockwise means velocity vector will be in this direction, right? So there is an electron present inside. So how do you apply? How do you find the direction of Lorentz force? Q into V vector cross B vector. So from V vector, you need to curl the fingers towards B vector. So since your fingers are going into the plane, then this would have been the direction of force. I repeat it again. V vector cross B vector, this is the direction of force. But this would have been the direction of force had the charged particle been positive, whereas you're dealing with electron. So electron will get drifted exactly in the opposite direction of your thumb. So electron goes to the other side and the positive side remains on the left. So O is positive and P is negative. This question, this kind of a question will also come. All these are unfortunately asked only in 1 month. That is where you lose. If 5 marks, you can easily write it. 1 mark is where they'll keep the checkpoint. So make sure your concept is clear. Okay. Those who are online, I hope you understood. Yeah.
Yes, sir.
Okay. So this is all about motional EMF as well. So the next concept that we are supposed to see is called as inductance, where we'll see self-inductance and mutual inductance. So for today, we'll stop with this. The next class, we'll have a look at inductance. So any doubts or any questions? No, right? Okay, we'll wind up.